professionalvmware.com vBrownBag. Tonight we have Vishal Misra and Jonathan Klick, who are both with Infinio, and they're going to be talking to us about conquering storage. I was promised that the title would make sense as we get into it. So Jonathan, you want to give us a little bit of background?
Absolutely, absolutely. So the idea here, of course, is talking about storage performance, and we're going to do kind of a combination of the science of storage performance as well as some of the practical stuff that you could use in the day-to-day. And then we kind of put a fun spin on this using the classic book of The Art of War as kind of a theme. So we'll see how it goes.
Cool. Awesome. Looking forward to it. For those that are new, or just need a reminder, you can hop on the conversation with us on Twitter using the vBrownBag hashtag. If you're not on Twitter for some reason, then get on or pop your questions into the GoToMeeting window. We've got, I've got to edit that out. We've got shows all over the place, APAC, EMEA, Latin America, here on our U.S. show. The recently paused OpenStack show that we should be kicking back up sometime over the summer, so ignore that bullet point. If you want to catch this or any of our other shows afterwards, you can find it on our website, professionalvmware.com, or on iTunes. We've got that nice short link there for you, bit.ly/brownbag iTunes, or if you're not an iTunes user, bit.ly.com/brownbag podcast. You can find Vishal and Jonathan both on Twitter. Got the nice full name Twitter handle so everyone can find them. And with that, I think I'm going to pop it over to you, Jonathan.
Awesome. Thank you.
You should be.
Yes, I have the full name Twitter handle, but the link. Oh, let me go ahead and see that. All right. Speed 2, and off we go. You'll be able to see it momentarily.
And I got you.
Perfect. Off we go. So as mentioned earlier, conquering storage performance, and we said with Sun Tzu, who is the author of The Art of War, which is kind of a classic book that people have used for ages now for business, politics, sports, any sort of place where there's competition and whatnot. But in any case, we're going to try to apply some of the principles found therein as well to storage performance. Kind of the battle plan and I guess the agenda going forward here is that we're going to talk about knowing what the enemy is, and then being able to track the enemy, and then finally talking about the cost of waging war against the enemy and how to be able to apply each of those. And those will make a lot more sense as we go through, of course. So first off, quote from Sun Tzu here: if you know the enemy and know yourself, you need not fear the results of 100 battles. And we know that we fight battles day in and day out against the likes of storage performance, and this is something that's very common. I think unless it's changed, the #1 source of support issues for VMware is still probably storage related. And in any case, this whole concept of knowing our enemy is not just about knowing them by name and saying, oh, that's Bob, he's my enemy. It's also about knowing, what does Bob eat for breakfast? Where does he go first thing in the morning? And being able to really kind of understand, applying this to storage performance, what are some of the key things that we need to know about storage performance to be able to effectively combat poor storage performance? So first of all, when I'm talking to people on a daily basis about this topic of storage performance, one of the things I do at Infinio as a systems engineer, basically there's these three kind of, I guess, measurements that come up a lot of times. We've got IOPS, we've got throughput, we've got latency, and people are looking at each of these as measurements of storage performance. And one of the things that I'm, of course, always teaching people about is this concept of how IOPS and throughput are more or less of a cause, while latency is kind of the effect. And what I mean by that is IOPS and throughput, of course, are a workload, and then latency is kind of a symptom of that. And for some of us, that's really a basic concept, but I think it's kind of worth mentioning going forward, because if we're trying to understand the enemy we're trying to combat here, that kind of distinction is really kind of significant. So when we talk about what latency is basically a time delay between cause and effect, kind of like we were mentioning earlier. And so when we're talking about this, really what we're talking about is, well, we've got kind of a cause, which is we've got an application, a virtual machine, that is requesting or making a storage request, and how long does it take for that application or virtual machine to be able to receive a response to that from the storage system. Now, this is where we get into some of the fun stuff. So when we're talking about latency, sometimes we talk about it in general terms, but there's a lot of different ways that we can measure latency, and it really kind of depends on where we're measuring latency from. If you're looking down the right side there, you've got application latency, you've got your perfmon metrics, you've got vSCSI metrics, and then of course you've got guest, kernel, and device latency, which really are kind of going to be the focus of this next little segment here. And what I mean by that is these are some of the primary metrics that we find in vCenter and ESX Top that helps us to understand and measure latency in our environments. Now, when we talk about guest latency, this is really kind of the complete latency that exists between your guests. Basically, if you ask a virtual machine, what's your latency like, that's what it's going to respond with. It's going to tell you that this is my guest latency. This is what I experience. However, guest latency has some subcomponents to it. And we've got kernel latency and device latency. Kernel latency, which is actually a superset of something that some of us might know as queue latency, basically is whenever a disk command sits inside the host, or the VM kernel for that matter, and not getting sent down the pipe to the storage system, that's a latency that can be experienced. And in a healthy environment, it's something we usually don't see too frequently, but it's a significant thing to note if you do see it. And then lastly, we've got this device latency here, which is basically when from the HBA or from the Ethernet port to the storage system and back again, that round trip latency is the device latency. And this is kind of your common latency, the sort of thing that you're going to see in just about any sort of environment, even if it's just a millisecond or two, and then upwards to much larger amounts, of course.
Hey, Jonathan?
Yes.
We can see the presenter mode that you're in. I don't know if you want to switch that up or on.
Sure, absolutely. Oh, it's sharing main screen for some reason.
There we go.
Yep.
I'll work some editing magic on the flip side.
Sure, no problem. So basically, when it comes to latency thresholds, this is kind of a significant detail because we just indicated there's all these different types of latency, and now you have to understand, okay, well, what latency is bad? If I'm looking at graphs in vCenter or ESX Top, well, not graphs in ESX Top, of course, but the idea is what should I be looking for? Well, there's a lot of rules of thumb. The one I'm displaying here is from our friend at Yellowbricks, Duncan Epping, and basically he's indicating that if you're looking at guest or device latency, which is GAVG and DAVG respectively, which is really kind of the metric that you'll see in ESX Top, but we'll talk about the vCenter manifestation as well. In any case, you're looking at about 25 milliseconds as kind of a rule of thumb to watch for. Now, of course, this is going to differ a little bit. There's different rules of thumb you'll see out there. In fact, even within VMware, you'll see that storage I/O control uses about a 40 millisecond threshold by default, and then likewise, storage DRS, I think the default threshold is about 15 milliseconds, by which it determines, okay, this is over 15 milliseconds. We need to do some load balancing. So those are rules of thumb. Once again, I can't emphasize it enough, because what it comes down to as well is that certain applications will, of course, be more sensitive to latency than others. And so that's something that you'll have to monitor separately. But otherwise, when you're kind of doing some monitoring or some proactive monitoring or other types of monitoring in your environment, these are some good metrics to be looking by with these thresholds that you're seeing in front of you. As mentioned earlier, when you're talking about kernel latency, which is represented as KAVG in this chart here, usually in a healthy environment, you're not seeing any. If you're getting up to a millisecond or two, it's worth noting, but not necessarily a concern. But of course, as you can see, the threshold is set pretty low for that. It's something that if you're starting to see that, something might be wrong, that there might be some excessive queuing taking place inside your host. So let's kind of put this all together. We've talked about the different types of latency. We've talked about the metrics, the thresholds involved in those. Let's use a practical example here that you might find within your own vCenter. So this is actually a screenshot I just took today in preparation for this from one of our own test labs. Basically, you'll note here that you've got the 4 different metrics. You've got command latency, which that's really your total latency metric or your guessed latency that we referred to earlier. Where before we referred to device latency inside vCenter, it's referred to as physical device command latency. And then you've got your kernel and queue latency as well. So in a typical healthy environment, as we mentioned, you'll see that kernel and queue latency pretty much flatline right around 0 for most of this graph. Likewise, because they're flatlining around 0, you're going to notice that your command latency as well as your device latency are pretty much synonymous. They're kind of overlaying one another in so much that you can't even tell that there's 2 separate lines for most of this. With a couple of minor exceptions, one of which being right there in the center of the graph, where you can see there's kind of a blue tip on top of that huge spike, where basically what happened at that point in time is there was not only a huge spike in device latency, there was actually a small amount of queue and kernel latency taking place as well that actually causes the total latency to spike above that. So in any case, this is a good example of what you might find in your own environments and what you could be looking for. The way I got here, by the way, is you'd visit your host inside vCenter. You would go to the Performance tab, go to Advanced, and then you would basically go into the chart options and go to your disk metrics and check those boxes for command latency, physical device command latency, kernel command latency, and queue command latency, all of which you should see in there. If you try to do it for something beyond real time, you may not be able to find those. It really kind of depends on how you set up your disk rollup, your disk metric rollup, or sorry, your performance metric rollups for your vCenter database. Virtual machine latencies. This is often a place where we'll go. We get complaints about an application. And naturally, we want to go and look at that application. We're not going to necessarily go and look specifically at the host. And so in these sorts of situations, we go to look for disk performance. There's really not a lot available to us. As mentioned earlier, the virtual machine really kind of only sees guessed latency or the total latency that it's experiencing. And so you're going to see this metric called highest latency. And this is going to be your way of being able to see is this guest actually experiencing latencies that are above a given threshold. You're not going to be able to break it down here into your kernel, queue, or device latencies. If you wanted to do that, you would need to go at the host level to be able to get that level of granularity and detail. As the last couple of points here, if you do prefer ESXtop, you like to use ESXtop, this is basically how you do it. You go into here, you hit V for virtual machines, and you can be able to see on the right side there, I kind of blurred out all the center stuff, not for secrecy by any means, but just simply to kind of keep the focus. But on the right side there, you can see your latencies for your reads and writes, and that'll all be there on a per VM basis. And then as well, if you wanted to see latencies on a disk adapter basis, that's available to you. And you can get down to, once again, to that granularity of device, kernel, queue, and so forth. If you're not too familiar with ESXtop and you're looking at these and you're thinking this would be useful, certainly I have a link there for Yellowbricks. In fact, there's a link to it right on their front page as well for ESXtop, and they've got a great guide that talks about the different metrics as well as instruction on how to be able to use ESXtop there. So I'm going to turn the time over to Vishal for some of his mad scientist work. Vishal, it's all yours.
Thanks, Jonathan. So yeah, I'll try some science here. I wear 2 hats. One hat is I'm the founder and CTO of Infinio, and my other hat is I am a professor of computer science at Columbia University. So what I'm going to talk about next is what sort of research has gone on in analyzing systems like these, and what is the academic point of view of what causes latency and what can you do about it. And one of the lessons that you learn when you try and understand and research these systems is that small things can make a big difference, both positively and negatively. So what do I mean by that? Let's go to the next slide. So this curve is critical to understand the relationship between load, latency, and how we can fight it. So first of all, latency is never linear, and the slide says it's exponential. What you see on the graph is on the x-axis, I'm plotting the load on a system, and on the y-axis is the latency or the response time from that system. Now this is a very generic graph. It applies to a wide variety of systems, including storage systems. It applies for routers, general computing systems, even caches. And the key there here is any system behaves well for a wide variety of load, but when things start going bad, they fall apart rapidly. There's always a knee to this curve. So somewhere around the point which is marked B on this curve, that's when things fall apart. And a small change in load can bring about a big change in latency. And when I say latency is not linear, it's exponential. Actually, the formula is latency is inversely proportional to the residual capacity of the system. So if your system is capable of processing, let's say, 100 requests per second, 100 IOPS, and the load that you're seeing is 90, 95, 99, then the residual capacity goes from 10, 5, 1. And the latency is the inverse of that. So as load increases, latency increases, and the relationship being inverse, it's not linear, it's highly nonlinear, it's exponential. So now let's try and understand what happens when things start going bad. Here, just to try and understand what's happening, I've pointed out 3 regions in this curve, the load latency curve, A, B, and C. So at C, we say the latency is low, the system is performing really well, and you're happy with the performance. Then point B is where things are starting to go bad. The latency is at that dangerous level. I think Jonathan mentioned something around 25 milliseconds. Things are starting to go bad. And A is where things are really bad. So things are falling apart, your applications are performing really badly, very poorly, your users are unhappy, and then you need to do something to improve the performance of the system so that your applications behave well and your users are happy. So the key here is we want to bring the load back from A to B and hopefully to C. Now, if you look at the load latency curve and you look at the difference in the latency between points A and B, that's this line AB. To bring about this reduction in latency, the amount of load that you need to reduce is this line with lowercase ab. So if you just compare the magnitudes of the 2 lines AB and AB, they are roughly similar. But when you go from point B to point C, the reduction in latency is small, but the reduction in load required to reach that point is quite big. So that is sort of the other side of the story, which says that when things go bad, things go really bad really rapidly. The other side of that story is there's a law of diminishing returns. When you offload the load, initially you're going to get a lot of benefit out of the offloading. But after a while you can offload a lot of load, but the amount of benefit that you get is not that much. The question is, what is it that you're trying to optimize here? What are your cost benefit trade-offs? And you have to kind of right size the amount of offload that you do to get the benefit. Now all caching solutions that are out there are all trying to do this thing, which they are trying to offload the load that is going to your storage system, so that the latency comes back under control. And whether you're doing SSD-based caching, server-side caching, write caching, read caching, DRAM-based caching, distributed caching, any kind of caching, all of them are doing one and only one thing. They're trying to reduce the load. So with the previous slide said, a small amount of fighting efficiently or fighting cleverly, that really says that, try and reduce the load by the right amount so you get the right benefit. Reducing the load by a lot may not get you the sort of proportionate benefit that you're looking for. So those the investment in resources should be smart, and that's the area that that we'll try to explain here, and that's what we're running with. So I'll turn it back to Jonathan now, and then we'll come back to this topic in a few slides.
Awesome, thank you, Vishal. That really kind of resonates really well with me. I saw that for the first time probably some months ago in recent times, and I can concur. That's what a lot of the customers I'm talking to are seeing, is that they're experiencing that at some point the gains that they're trying to get are basically the amount of cost and effort they're putting into that becomes greater and greater for smaller and smaller gains. And so this kind of leads us into this topic, though, of the cost of waging war against latency, against poor storage performance. And another little Sun Tzu quote here, which is, who wishes to fight must first count the cost. So kind of introducing this topic, this next segment here with the cost, we've got these this kind of Siamese twins here of the we're called the odd couple of storage. The idea here is that we've got these two different aspects of storage. We've got the performance aspect and we've got the capacity aspect. On one end, we're able to fit so many gigabytes and terabytes. On the other end, we're able to support so many IOPS. And this can wildly differ depending on the disk types we have, the storage technologies we're leveraging. And as some extreme examples here, we have an example of where you've got 50 gigabytes of capacity and you could support 500 IOPS. If you filled up that 50 gigs really quick, which we know is possible, and you never hit your performance capacity, well, guess what? Then you have all this extra performance that you don't need. On the reverse side, you could have lots more capacity and find yourself with lots of extra capacity while you've already hit your 200 IOPS that you can sustain while not experiencing those adverse latencies that we talked about earlier. And so this is a problem that I think a lot of us are experiencing. And so we've got this topic of what we call server-side caching that's pretty hot now in the industry. There's lots of vendors trying to do that. And they're trying to do this, which is decoupling capacity and performance. Now, I want to keep in mind that there was no penguins harmed in the making of this presentation. But the idea here is that if we do kind of segregate these two, if we then say, let's buy capacity when we need capacity, and let's buy performance when we need performance, it allows us to be able to go ahead and basically get more performance when we need it, like we're seeing here. Let's tack on another 1,000 IOPS worth of capacity, and this is really kind of where server-side caching is able to kind of help balance out that equation. So what we're seeing right now in the marketplace is there's a lot of different flavors of server-side caching. In fact, many of you, hopefully many of you, are already familiar with those. So for example, there's kind of this hot thing going on now with server-side SAN. You've got vSAN, which is like a huge buzz right now, people talking about it. You've got Atlantis actually just came out with a technology that kind of complements vSAN as well. And so there's definitely different technologies on the server-side SAN type technologies. Additionally, you've got server-side caching with Flash. There's actually a plethora of vendors out there that are trying to provide that. One of the ones that we've known for a long time is Fusion.io, and then there's been lots of other technologies coming along since then that are allowing you to use Flash to be able to once again, decouple performance from capacity, providing you the performance in the server side, allowing you to kind of scale your the performance of your storage while your server tier continues to grow. You add more VMs, and eventually add more hosts. Well, guess what? You expand out your caching tier there to be able to accommodate for that, while your storage system kind of remains the same. And then likewise, there's other vendors out there that are trying to solve this problem by using server-side caching with RAM. So rather than installing SSDs or PCIe cards in your hosts, they leverage latent memory that may exist in your hosts to be able to provide that same level of experience. And so I guess I'll turn it back over to Vishal to talk about a little bit of the deeper dive architecture type side of things when it comes to server-side caching.
Thanks, Jonathan. So even though there were some complaints on Twitter that we are dropping math, or more accurately science, I'm going to drop a little bit more science here. So what we saw earlier when I was talking about was the relationship between latency and load, and you could say that's sort of driven by or analyzed using queuing theory. There are two other theories that are very important here, and I'll tell you how that goes into a design of an architecture that can do very efficient caching. So what you see here is we have this blue blob in front of the NAS, and that is a pooled cache. So what you see here is all the RAM in each server that's assigned to a cache, that has been pulled together into one unified, you can say one global namespace cache. And you know, in the previous slide where I was talking about the load latency relationship, I said, you know, a small amount of cache can make a huge difference. Now what I'm going to talk about is how a small amount of cache can appear as a large amount of cache by, you know, smart architectural choices. So what happens when you pull together all of these individual server RAM caches into one shared distributed cache? Well, the theory that applies here is the theory which we work with in networking called statistical multiplexing. And the idea there is that, you know, different servers will go through their own individual peaks and troughs of workload. Sometimes some servers are going to be idle, sometimes other servers are going to be very busy, and the hope is that they are not simultaneously all peak busy. Now it might happen sometimes. Suppose your server farm is, you know, doing web serving and there's some flash event. Those kind of things can happen. But in general, the way the loads are spread out, there is some amount of statistical multiplexing going on. All servers are not simultaneously busy all the time. So the effect of that is, even though we are sharing this cache across all servers, let's say you have n servers and they have all pooled in their share. Theoretically, each server should see 1/nth of the pooled cache, but because of statistical multiplexing, they actually see a much bigger cache. When some servers are idle, they are not using up their share of the cache, and that automatically goes into the usage of the other servers that are busy. So that's one aspect. Sharing and pooling and having a distributed cache actually amplifies what an individual server sees because of statistical multiplexing. The other thing that an architecture like this can exploit is that of deduping. Now, deduping is, you can say it's sort of a compression technique, and information theory tells us that the larger the working set that you have, the better are the chances of achieving compression. So if you have only a small text file, compressing it won't bring you any benefit. But if you have a huge text file, then compressing it gives you huge benefits, and it reduces the average size of that file to the entropy of, you can say, the English language. So the same sort of principle applies here. When you dedupe across servers, then your deduping efficiency goes higher. Just take a simple case. Let's say you're dealing with virtual machines. Each one of them has a boot sequence. Now, if your cache is looking at only one server, the boot sequence might appear once, might appear 5 times, might appear 8 times, depending on the number of VMs that server has. But if you look across all these servers, now your boot sequence has to appear only once for 500 servers. So your deduping efficiency suddenly increases. So that's the other thing that a shared distributed cache can exploit, which is doing a global deduping across all servers. When you do that, suddenly the small amount of resources that you put in every server becomes much more amplified. And again, I repeat, there are two effects that are causing this architecture to present a much bigger cache to the server than the actual physical resources. And the two effects are statistical multiplexing, where the servers go up and down in their usage of the cache. And the second is this increase in efficiency of deduping as you look across a larger set of VMs or a larger set of working sets to do your deduping. So that's sort of the principle that is behind the architecture of Infinio, as well as what Atlantis introduced yesterday. As far as I can tell, they are doing something similar when they developed this RAM-based storage device. I think they're doing deduping across servers, and that really helps. That's a very smart architectural choice. Jonathan?
Thank you, Vishal. That was a really good overview of a good caching architecture. So that being said, let's go ahead and wrap this up. So in the end, kind of thinking back to Vishal's science, it's math, the math that made our heads hurt, I'm sure. The idea here is that it's really about applying the amount of cost and effort it takes to be able to solve the amount of I/O workload that you're trying to reduce, or the amount of latency you're trying to reduce. And so we've got a lot of options available to us. Some cases, getting a new storage system makes sense. And however, if we can, going down this tree right here, it gets less and less expensive to be able to solve a given problem depending on the amount of performance we need. And so I don't need to read this to you, but suffice it to say, we've got a lot of options now. In fact, for any of you who go to vMugs or things like that nowadays, it seems like there's a ton of vendors out there, particularly startups, who are all trying to solve storage problems in different ways. So the good news is there's a lot of options. Unfortunately, it's a lot of work on our part to be able to kind of evaluate solutions and find the best ones that meet kind of our cost to performance ratio. In the end, bad storage performance is our enemy. That's kind of a no-brainer. It almost doesn't even need a bullet. However, latency is really kind of the best way to monitor the enemy, and there's a lot of different types of latency that we have to be aware of. As Vishal was talking about, those small I/O reductions sometimes can provide a large latency improvement, and we get those diminishing returns as we continue to try to get better and better storage latencies. We'll have to exert more and more effort and cost to be able to reduce that. And then lastly, we've got this topic of server-side caching that can help you decouple storage performance from capacity and hopefully without harming any penguins. So that's the end. I think we made it within the time guidelines we were given. Questions, thoughts, complaints, anything that anyone might have?
More math.
More math.
We've got finished up in a nice amount of time. We've got no questions in GoToMeeting right now. A lot of conversation on Twitter, though. If anyone wants to come on and ask a question, raise your hand and I can unmute you. We prefer barking dogs and screaming kids in the background if you do want to be unmuted, so just keep that in mind.
We give barking dogs and screaming kids a priority.
One question popped up. Michael, do you want me to unmute you or just reread your question? Michael asked in the GoToMeeting window, what types of software are out there for server-side caching?
Okay, yeah, there's a lot of different solutions out there, as I indicated earlier. Let me go ahead and just rattle off some of them. The first and foremost, kind of a no-brainer, is ourselves, Infinio. We're really big proponents of the server-side caching movement, and of course we believe we're doing it the best way possible, and we're confident in that. But there's a lot of other vendors that we're seeing that kind of compete with us in that regard out there. So you've got Atlantis, who, of course, they had a new product offering they just announced recently. Before that, they were primarily focused on VDI. I get the impression they're going to be stepping out and just supporting virtual servers as well. And then likewise, in that same sort of space, trying to support VDI on the server-side caching, you have Liquidware. Liquidware Labs is actually stepping in that with a new technology I think they're calling FlexIO. Then when you're moving into using a combination, moving into more of using flash rather than RAM for caching, you've got PernixData, who's out there. They're kind of a hot vendor. And then you also have, in fact, many of you might know Frank Deneman, and he's of course over there at Pernix now. And then you've got Proximal Data, so don't get that confused with Pernix. And then you also have, SanDisk is jumping into this with FlashSoft. I think FlashSoft was an acquisition of theirs, and I'm trying to think of other ones off the top of my head, but that's really kind of a lot of the front runners, I think, out there that you probably would be at the top of your list of ones to investigate.
Yeah, and Jonathan, I would add, this is Matt Brender, that the vBrownBag's own Kyle Murley works at Proximal, if you're interested in hearing their angle of it. And then also Fusion.io, while they provide the PCIe cards, they also recently acquired IO Turbine, which allows them to do some server-side caching.
Awesome. And yeah, somebody just brought up there's also VMware's own caching solution, vSphere Flash Read Cache. I always have to try not to say vFlash when I read that.
Yeah, Flash. And then for their VDI solution, they have CBRC, which I believe has a secondary name as well.
It's called VSA now, I think. CBRC is renamed as VSA.
View Storage Accelerator?
Yeah.
Yeah, so the CBRC and vFlash, well, CBRC is of course is built right into the hypervisor for the likes of View, I believe. I think it needs to be enabled or something like that. And then likewise, vFlash, of course, is only available in 5.5, so maybe motivation to upgrade to 5.5. But vSphere Flash Read Cache is also for Enterprise Plus licensing only, I think.
Yep.
So if you happen to have Enterprise Plus licensing, definitely something to take a look at.
Alan wanted to check in and make sure the Penguins were okay.
They are. It was a consensual agreement. They are happy now that they're living their own separate lives. They're both married. It's great.
Well, maybe the sword didn't hurt them, but it's questionable what the math did to them.
Awesome. So it's I'll throw it out there one last time. Get your questions in. Otherwise, I can start letting my computer chug away on the recording and hopefully get this up for the folks that weren't able to watch live. Anyone else out there? Last call. Anyone? Penguins driving? Nope. He's offline.
Yeah, Jonathan, I would just want to throw out there that you'll see a theme that there's a little Mobius strip icon floating in there for Infinio systems because Jonathan, Vishal, and I are all from there. We wanted to give some useful information to the community and stay pretty far away from getting down to a pure vendor pitch. If you are interested in the product at all, though, after this, we're very active on Twitter and Spiceworks and other social sites. We'd love to hear from you if you're interested in getting it in your lab or in a test environment or production, for that matter.
Awesome. with that, I think we'll hit the stop recording button.